Uranus is the most bizarre planet in our solar system, and these are the facts that explain exactly why. From rolling sideways around the sun, to smelling like rotten eggs, to potentially raining diamonds in its interior, this is one world that breaks nearly every expectation we have about what a planet is supposed to be. Hit the like button, subscribe if you haven't yet, drop a comment telling me where you're watching from and what you're up to right now. Honestly, I love seeing who's out there. Now let's get into it. To understand why Uranus is so strange, you first have to understand where it sits in our cosmic neighborhood. The solar system contains 8 planets, and for most of human history, people only knew about 5 of them: Mercury, Venus, Mars, Jupiter, and Saturn, because those are the ones visible to the naked eye on a clear night. Uranus changed that. It was the first planet ever discovered with the aid of a telescope, and the man who found it wasn't even looking for it. On the night of March 13, 1781, a German-born British astronomer named William Herschel was standing in his garden at 19 New King Street in the city of Bath, England, sweeping the sky methodically, cataloguing stars. Herschel wasn't a career astronomer in the traditional sense. Born Friedrich Wilhelm Herschel on November 15, 1738, in Hanover, Germany, he had spent much of his adult life as a musician, a composer and organist who happened to develop an obsessive love of stargazing on the side. By the time he was in his early 40s, his homemade telescopes were among the finest in England, and night after night he charted the heavens with a patience and precision that professional astronomers of the era envied. That March night, something caught his attention. There was an object that looked slightly different. Not a sharp pinpoint of light like a star, but something that appeared to have a tiny disk when he increased the magnification. Herschel noted it in his journal, and at first concluded it was probably a comet. He reported it as such. The problem was, it didn't behave like a comet. It moved too slowly, it had no tail, and as other astronomers began tracking it, its orbit turned out to be nearly circular rather than the elongated ellipses that comets follow. Within months, the astronomical community reached a stunning conclusion. William Herschel had discovered a new planet, the first addition to the known solar system in recorded history, sitting out there at a distance nobody had seriously mapped before. Herschel became famous overnight. King George III of Britain, who was quite interested in astronomy himself, summoned Herschel and gave him a royal appointment and a salary to pursue his work full-time. Herschel, naturally grateful, proposed naming the new planet Georgium Sidus, Latin for the Georgian star, in honor of the king. The British used that name for decades. French astronomers, perhaps unsurprisingly given the political climate between Britain and France, refused to name anything after the British monarch and called it Herschel instead. It was a German astronomer, Johann Elert Bode, who proposed in 1782 the name we use today, Uranus, after the ancient Greek deity of the sky, the primordial father of the Titans. That name stuck, and by the middle of the 19th century, it was standard everywhere. Herschel was eventually knighted by the king, Sir William Herschel, and he died on August 25, 1822, in Slough, England, having spent his final years continuing to map the cosmos from his garden. Here's an interesting wrinkle to the discovery story. Uranus had actually been seen before, repeatedly, by astronomers who simply didn't recognize what they were looking at. The English astronomer John Flamsteed observed it as early as 1690 and logged it as a star, cataloguing it under the designation 34 Tauri. Others recorded it over the following decades, all of them assuming it was just another faint fixed star. Under a very dark sky with good eyesight, Uranus is technically visible without a telescope. Its apparent magnitude ranges from about 5.3 to 5.9, right at the edge of naked eye visibility. But it moves so slowly across the sky, taking 84 Earth years to complete one full orbit, that you'd need to watch it for weeks before noticing any movement. Without a telescope to reveal its disk, there was no reason for anyone to suspect it was anything other than a dim, unremarkable star. Herschel's telescope made the difference, and that's what changed history. The planet itself, once we actually got to study it properly, turned out to be unlike anything else in our solar system. Let's start with the basics, and then work our way into the truly weird. Uranus is the 7th planet from the Sun, sitting at an average distance of approximately 2.87 billion kilometers from our star, about 19.2 times the Earth-Sun distance. Light from the Sun, which reaches Earth in about 8 minutes, takes approximately 2 hours and 40 minutes to get to Uranus. Distances at this scale start to feel abstract, so consider it this way. If you drove at highway speed without stopping, it would take you something like 3,000 years to get there. In terms of size, Uranus ranks 4th in the solar system by diameter. Its equatorial width measures about 51,118 kilometers, which is roughly 4 times the width of Earth. You could fit approximately 63 Earths inside its volume. Its mass comes in at about 14.5 times Earth's mass, placing it 3rd among the planets in that category. And yet, despite that size, the gravity at Uranus's cloud tops is only about 91% of Earth's surface gravity, meaning if you weighed 68 kilograms on Earth, you'd weigh slightly less on Uranus. That might seem counterintuitive for a planet so much larger, but it comes down to density. Uranus is made primarily of gases and ices, spread across a much larger volume, so its average density is considerably lower than rocky, compact Earth. The word ices needs a bit of explanation, because it doesn't mean what you might picture. When planetary scientists call Uranus an ice giant, a category it shares with Neptune and which distinguishes it from the gas giants Jupiter and Saturn, they're referring to the chemical composition, not the physical state. The ices in Uranus's interior, primarily water, methane, and ammonia, aren't frozen solids. Under the pressures and temperatures that exist deep inside the planet, these compounds exist as hot, dense, electrically conducting fluids. Think of it more like an incredibly compressed, scalding ocean of exotic chemistry than anything resembling the ice in your freezer. Gas giants like Jupiter and Saturn are overwhelmingly hydrogen and helium, with very little of this heavier icy material. Uranus and Neptune have a different recipe entirely, with higher proportions of these heavier compounds and relatively smaller cores and gas envelopes. That distinction matters enormously for understanding how they formed and why they behave so differently from their larger cousins. The atmosphere of Uranus, which is what we actually see when we look at the planet, is composed mainly of hydrogen, about 83%, along with roughly 15% helium and about 2.3% methane. That methane is the key to the planet's color. Methane molecules absorb red wavelengths of light and reflect back blue and green wavelengths, which is why Uranus appears that distinctive pale cyan, a blue-green that sets it apart from most objects in the solar system. It's actually a rather beautiful color, serene and almost eerie in photographs, like a marble dropped into space. Deeper in the atmosphere, there are clouds composed of different compounds at different levels. Methane ice clouds higher up, water and ammonia clouds at much deeper, hotter levels that we can't directly see from space. Wind speeds in Uranus's atmosphere can reach approximately 900 kilometers per hour, comparable to Neptune's extreme winds, though cloud features on Uranus are notoriously hard to see and track. During the Voyager 2 flyby in 1986, the planet looked almost featureless, a plain blue-green ball with almost no visible storms or bands. Scientists weren't sure what to make of that at first. As more time passed and better telescopes became available, particularly the Hubble Space Telescope and ground-based observatories using adaptive optics, it became clear that Uranus does have weather and atmospheric activity, but it's subtle and seasonal in ways that depend heavily on where the planet is in its 84-year orbit. Which brings us to the thing that makes Uranus unlike anything else in the solar system: the axial tilt. Every planet rotates on an axis, an imaginary line running through its poles. Most planets tilt slightly relative to their orbital plane around the Sun. Earth tilts about 23.5 degrees, which is what gives us our 4 seasons. Mars tilts about 25 degrees, similar to Earth. Saturn tilts about 26.7 degrees. Jupiter, at only 3.1 degrees, barely tilts at all, which is why its seasons are almost non-existent. Even Venus, which rotates backward compared to most planets, has a tilt of about 177.4 degrees. Uranus tilts 97.77 degrees. 97.77 degrees. The orbital plane, the flat plane in which Uranus orbits the Sun, is nearly identical to the equatorial plane. The planet essentially rolls around the Sun on its side, like a ball rolling across a table rather than spinning upright like a top. If you tilted your own head 97 degrees to the right, you'd be looking almost sideways at the floor. That's the angle Uranus travels through space. The implications of this for what life would experience on Uranus, if anything could survive there, are almost surreal. During the summer solstice at Uranus's north pole, the sun sits almost directly overhead and circles around the sky without setting for 42 straight Earth years. For 42 years of continuous daylight, and then, as the planet completes half its orbit, a 42-year-long night falls on that same pole. Meanwhile, the opposite pole swings into 42 years of sunlight. The seasons each last roughly 21 Earth years. The equatorial regions, by contrast, get relatively brief periods of day and night during the portions of the orbit when neither pole points at the sun, but even that is wildly different from anything on Earth. What caused this? The leading explanation, supported by computer simulations and physical modeling, is a collision. Very early in the solar system's history, roughly 4 billion years ago, when the planets were still forming and the region was a chaotic place filled with leftover material, something very large, estimated to be roughly the size of Earth, struck Uranus at an angle and knocked it onto its side. The impact hypothesis fits the available evidence reasonably well, and a 2018 study from Durham University in the UK ran detailed simulations suggesting the impactor was indeed roughly Earth-sized and struck at an oblique angle, which would explain both the tilt and several other characteristics of the planet, including why Uranus's moons orbit in the same tilted plane as the planet's equator. Whatever hit it must have been large enough and oblique enough to tip the whole planet over permanently, and the moons that either existed at the time or formed from the collision debris have been orbiting in the resulting tilted configuration ever since. There's a fascinating secondary consequence of this tilt that has puzzled scientists for decades. You would expect, if the sun shines directly on one of Uranus's poles for 42 years, that the polar region would heat up dramatically compared to the equator. The pole in perpetual darkness should be extremely cold. The equator, which only sees the sun during the equivalent of Uranian spring and autumn, should be somewhere in between. But that's not what measurements show. The temperature across Uranus's atmosphere, from pole to equator, is surprisingly uniform. The planet seems to mix and redistribute its heat in ways that aren't fully understood. And the fact that Uranus radiates almost no internal heat at all makes this even more puzzling. We'll come back to that. The planet's rotation period, the length of its day, adds another layer of strangeness. Uranus takes approximately 17 hours and 14 minutes to complete one rotation. But here's the twist. Because it's tilted 97.77 degrees, a day on Uranus means something profoundly different depending on where you are on the planet and where Uranus is in its orbit. During a solstice, the pole facing the sun is experiencing one 84-year-long day in the sense of continuous sunlight, while in other parts of the planet, the 17-hour rotation doesn't produce meaningful day-night cycles because the sun's movement overhead is dominated by the slow seasonal shift rather than the quick spin. Timekeeping on Uranus would require an entirely different conceptual framework than anything we use on Earth. Let's talk about the temperature, because this is one of Uranus's most mysterious properties. At the cloud tops, the effective temperature of Uranus is approximately -224 degrees Celsius, which translates to -371 degrees Fahrenheit. That makes Uranus's atmosphere the coldest of any planetary atmosphere in the solar system, colder even than Neptune, which orbits much farther from the Sun. Neptune's average cloud-top temperature is around -218 degrees Celsius, still brutally cold, but measurably warmer than Uranus. Why is the father planet warmer than Uranus? This is one of the most intriguing unanswered questions in planetary science. Part of the answer lies in internal heat. All the giant planets in our solar system generate more heat internally than they receive from the Sun, and they radiate this excess heat outward. Jupiter radiates about 1.7 times more energy than it receives from the Sun. Saturn radiates about 1.8 times more. Neptune radiates about 2.6 times more energy than it gets from sunlight. Uranus radiates essentially the same amount of energy it receives from the Sun. It has, for all practical purposes, no detectable internal heat source, or at minimum, an internal heat source so weak it barely registers. That is deeply strange. The other giant planets are still releasing heat left over from their formation, when the gravitational compression of gas and rock and ice generated enormous amounts of energy. Over billions of years, that primordial heat slowly leaks out. And for Jupiter, Saturn, and Neptune, it's still leaking out in measurable amounts. For Uranus, something seems to be preventing that heat from reaching the surface. Several theories have been proposed. One is that a stable layer in the deep interior acts like a thermal blanket, trapping the internal heat and preventing it from convecting upward. Another possibility is that the giant impact that tilted the planet also had some effect on the internal structure that disrupted normal heat flow. A third possibility is that some combination of atmospheric layering, perhaps involving a dense methane ocean layer acting as an insulator, prevents heat from rising. No consensus has emerged. For now, Uranus keeps its warmth to itself, buried in a cold interior, while its cloud tops remain the coldest in the solar system. The magnetic field of Uranus is another entry in the catalogue of weirdness. Every planet with a significant magnetic field generates it through some mechanism in its interior, typically the movement of electrically conductive fluid. On Earth, that's molten iron in the outer core. Uranus has a magnetic field, but it's structured in a way that nobody expected. Most planetary magnetic fields are roughly aligned with the planet's rotational axis. Earth's magnetic axis is tilted about 11 degrees off its rotational axis, which is why compasses don't point exactly at the geographic North Pole. That's a modest misalignment. On Uranus, the magnetic axis is tilted about 59 degrees away from the rotational axis. To picture that, imagine a compass on Earth that pointed not north or slightly off north, but nearly northeast-southeast. On top of that, the magnetic field isn't centered at the middle of the planet. It's offset from the center by about 1/3 of the planet's radius, sitting closer to one side than the other. The result is a magnetic field that wobbles and tumbles wildly as the planet rotates. Because the rotational axis is itself tilted 97.77 degrees relative to the orbital plane, the combined effect of the rotation, the axial tilt, and the off-center magnetic field produces a magnetosphere that is, in the words of one researcher, like a corkscrew tumbling through space. The shape and orientation of the magnetic bubble surrounding Uranus changes dramatically every 17 hours as the planet rotates, which is completely unlike anything seen elsewhere in the solar system. Scientists believe that Uranus's magnetic field is generated not in a metallic core, as on Earth, but in the icy, electrically conductive mantle, the layer of compressed water, ammonia, and methane above the core. This is consistent with Neptune's similarly unusual magnetic field, suggesting this type of slush dynamo might be characteristic of ice giants in general, distinct from both the rocky planet magnetic fields, like Earth's iron core, and the metallic hydrogen dynamos in gas giants like Jupiter. In 2020, scientists went back to data collected by Voyager 2 during its 1986 flyby, and made a discovery that had been hidden in the numbers for over 3 decades. A team led by Gina DiBraccio at NASA Goddard Space Flight Center, publishing in Geophysical Research Letters, found that Voyager 2 had flown through a plasmoid, a large bubble of plasma containing charged particles that had been ejected from Uranus's magnetosphere. Plasmoids are known to occur at other planets, but this was the first time one had been identified at Uranus. The plasmoid carried material from Uranus's atmosphere out into space, hinting that the planet's magnetosphere plays an active role in atmospheric escape, and suggesting that there may be much more happening in and around Uranus than those early Voyager images led us to believe. Now let's talk about the rings, because Uranus's ring system is one of the more dramatic examples of scientific discovery by accident. On March 10, 1977, just 4 years before Voyager 2 launched, and 9 years before it arrived at Uranus, a team of astronomers led by James Elliott at Cornell University made a startling discovery while watching Uranus pass in front of a distant star, an event called an occultation. The plan was to use the occultation to precisely measure Uranus's diameter and study its atmosphere by watching how the star's light dimmed as the planet's edge moved across it. But something unexpected happened. Before Uranus reached the star's light flickered several times in quick succession, then stayed steady. Then Uranus blocked it completely. And then after Uranus moved past, the star flickered the same way again, in reverse. Those flickers were rings. The narrow rings of Uranus, one by one, passed across the star and briefly blocked its light, first on one side of the planet, then on the other, revealing a ring system that nobody had suspected existed. The discovery was immediately recognized as significant, and follow-up observations confirmed it. Uranus has 13 known rings, all of them narrow and extremely dark. That darkness is notable. The rings reflect only about 2 to 3% of the light that hits them, making them among the darkest objects in the entire solar system. Coal, which we think of as black, typically reflects around 4% of light. Uranus's rings are darker than coal. The rings are named using a combination of numbers and Greek letters: 6, 5, 4, alpha, beta, eta, gamma, delta, lambda, epsilon, nu, mu, and zeta. The epsilon ring is the widest and brightest of the group, though bright here is a relative term. They're thought to be composed of dark, rocky material, possibly organic compounds that have been darkened by radiation over billions of years. One leading hypothesis is that the rings are remnants of moons or other bodies that were broken apart by collisions or by Uranus's tidal forces, the same gravitational stretching forces that keep the rings of Saturn organized. Whatever they once were, they're now a collection of narrow bands of debris orbiting in tight formation around the planet, in the same tilted plane as everything else in the Uranian system. 2 additional faint outer rings were discovered much later, revealed by the Hubble Space Telescope in 2005. Those outer rings, designated Mu and Nu, are broader and more diffuse than the inner rings, and Mu is actually slightly blue in color, unlike the others, possibly because it's made of finer, smaller particles that scatter light differently. The moons of Uranus deserve their own chapter in this story, partly because of how many there are, partly because of the names they carry, and partly because of just how strange some of them turn out to be. Uranus has 27 known moons, and every single one of them is named after a character from the works of William Shakespeare or the poet Alexander Pope. This is unique in the solar system. Every other planet names its moons after figures from Greek, Roman, or Norse mythology. Uranus is the literary exception. The tradition started when Herschel discovered the first 2 moons, Titania and Oberon, in 1787, naming them after characters from Shakespeare's A Midsummer Night's Dream. The pattern continued as more moons were found over the centuries, and now the full roster includes names like Miranda, Ariel, Umbriel, Caliban, Sycorax, Prospero, Setebos, Stefano, Trinculo, Francisca, Margaret, Ferdinand, Perdita, Mab, and Cupid, a roll call of Shakespearean characters and creatures that gives the Uranian system a literary personality entirely its own. The 5 major moons are Miranda, Ariel, Umbriel, Titania, and Oberon. Titania, the largest of the group, has a diameter of about 1,578 kilometers, roughly half the size of Earth's moon. Oberon, the second largest, measures about 1,523 kilometers across. These 2 were discovered by Herschel himself in 1787, just 6 years after he found the planet. Ariel and Umbriel were found by William Herschel in 1851, and Miranda was discovered by Gerard Kuiper in 1948. Of the 5, Miranda might be the most scientifically fascinating because it may be the most visually dramatic world in the solar system. It's the smallest of the 5 major moons, only about 472 kilometers in diameter, but its surface is one of the most varied and extreme places we've ever seen. Voyager 2's images of Miranda revealed a world that looks as if it was assembled from mismatched puzzle pieces. Smooth, rolling plains sit next to towering cliffs and deep canyons, chevron-shaped formations called coronae, and ancient cratered terrain all jumbled together. One theory is that Miranda was completely shattered by an ancient collision, and the pieces gradually reassembled themselves under gravity, creating the patchwork landscape we see today. Whether or not that's the correct explanation, what's beyond debate is the geology, or rather the iceology, that Voyager 2 captured. The most striking feature on Miranda is Verona Rupes, a cliff face so tall it would make the Grand Canyon look like a sidewalk curb. Estimates of Verona Rupes' height range from about 5 kilometers to as much as 10 to 20 kilometers, depending on the measurement method used. To put even the conservative estimate in perspective, Mount Everest rises about 8.8 kilometers above sea level. Verona Rupes could be taller than Everest by a significant margin, and because Miranda's gravity is only about 0.8% of Earth's gravity, an object dropped off the top of that cliff would take roughly 10 minutes to reach the bottom. Someone falling off that cliff, assuming they somehow survived the airless -200-degree environment, would fall long enough to recite substantial poetry on the way down. It's one of the most extreme geological structures in the known solar system. Ariel shows signs of geological activity in its past, with bright, freshly resurfaced terrain and long systems of valleys that may have been carved by liquid water or ice flowing along fault lines billions of years ago. Umbriel, by contrast, is the darkest and oldest looking of the 5 major moons, its surface heavily cratered and coated in something dark and ancient. One mysterious feature on Umbriel is a bright ring visible on its floor. Scientists have debated what caused it. Oberon also shows heavy cratering, along with a mountain on its limb, the edge of the visible disk, that rises about 6 kilometers above the surrounding terrain. Beyond the 5 major moons, Uranus has 22 smaller moons, most discovered in recent decades using Earth-based telescopes or Hubble. Some of them, like Caliban and Sycorax, are thought to be captured objects, bodies from the outer solar system that wandered too close to Uranus and were pulled into orbit by its gravity. Their orbits are irregular, meaning they don't follow the neat, tilted equatorial plane arrangement of the regular moons. Instead, they orbit at high inclinations and sometimes in retrograde directions, carrying the signatures of their chaotic, captured origins. Only one spacecraft has ever visited Uranus. Just one. Despite everything we've described, the bizarre axial tilt, the cold atmosphere, the tumbling magnetic field, the dark rings, the extraordinary moons, the unanswered questions piling up, humanity has sent exactly one mission to this planet, and it flew past without slowing down. That mission was Voyager 2, and its story deserves to be told carefully, because it's one of the great achievements in the history of space exploration, even if Uranus wasn't actually the primary destination. Voyager 2 launched on August 20, 1977, from Cape Canaveral, Florida. Its twin, Voyager 1, launched about 2 weeks later, on September 5, 1977. But Voyager 1 was placed on a faster trajectory and actually reached Jupiter first, despite launching second. The Voyager program was designed to take advantage of a rare planetary alignment, a configuration that occurs only once every 176 years, where the outer planets would be arranged in a way that allowed a single spacecraft to visit multiple planets by using each planet's gravity to slingshot toward the next. Voyager 2 was designed to take the slower, more comprehensive path: Jupiter, Saturn, Uranus, and Neptune. The flyby of Uranus happened on January 24, 1986, just over 8 years after launch. The spacecraft came within approximately 81,500 kilometers of Uranus's cloud tops, close enough to take detailed images and make measurements, but not so close as to be captured by the planet's gravity. The encounter lasted only a matter of hours in terms of the closest approach phase, though the instruments were operating for days before and after. What Voyager 2 found was revelatory, and it was also puzzling in ways that have occupied planetary scientists ever since. The images, once processed back on Earth, showed a planet that looked almost featureless, that smooth blue-green marble with barely a cloud in sight. The axial tilt was confirmed and measured precisely. The magnetic field, wildly tilted and off-center, was mapped for the first time. Voyager 2 discovered 10 moons that hadn't been known before, bringing the count to 15 at the time. It found 2 new rings, and it captured those first detailed images of the 5 major moons, revealing Miranda's impossible cliffs and Ariel's bright resurfaced valleys. All of this happened during those few hours of closest approach on January 24, 1986, and the data collected that day has been mined by scientists for decades afterward, including that plasmoid discovery in 2020, found by reanalyzing the original magnetometer data 34 years later. Voyager 2 then continued on its way to Neptune, which it reached in August 1989, before continuing out of the solar system entirely. As of late 2018, Voyager 2 crossed the heliopause, the boundary between the solar wind and interstellar space, and is now traveling through interstellar space, one of only 5 human-made objects to have left the solar system. It still transmits data back to Earth, though the signal is faint and travels at the speed of light from an ever-increasing distance. No spacecraft has been sent back to Uranus since. The planet has been observed from Earth and from the Hubble Space Telescope, which has provided some remarkable data, especially as Uranus moved toward its equinox in the early 2000s, and storms began appearing. In 2006, Hubble imaged a dark spot on Uranus, similar to the Great Dark Spot periodically seen on Neptune, evidence that Uranus can generate large storm systems under the right conditions. In 2014, astronomers using the Keck Observatory in Hawaii observed a series of bright, powerful storms erupting on Uranus, the most intense activity seen in years, generated by seasonal changes as the planet's northern hemisphere moved into more direct sunlight. The fact that we've only had one flyby, over 35 years ago, has become a point of significant discussion in the planetary science community. The reality is that Uranus has been a relatively low priority in mission planning compared to planets and bodies considered more immediately relevant to questions about life in the solar system. Mars exploration has dominated budgets for decades. Jupiter's moon Europa, with its subsurface ocean, has attracted enormous attention. Saturn's moon Enceladus has its own active geysers. Against these targets, an ice giant nobody can directly visit has been hard to prioritize. That is changing. In April 2022, the National Academies of Sciences, Engineering, and Medicine published the Planetary Science and Astrobiology Decadal Survey, the most important document in American planetary science, published every 10 years to set priorities for the coming decade. The 2023-2032 survey ranked a Uranus Orbiter and Probe as the highest priority new flagship mission for NASA. Not second priority, not third, number one. After years of relative neglect, the planetary science community voted with their recommendations to send a dedicated spacecraft to orbit Uranus, study it over an extended period, and drop a probe into its atmosphere to directly sample its composition. A launch window in the early 2030s would allow the mission to use a gravitational assist from Jupiter, which would be necessary to reach Uranus in a reasonable time frame. If launched in that window, the spacecraft would reach Uranus roughly 13 years after launch, arriving sometime in the mid-2040s. The probe that enters the atmosphere would transmit data until the pressure crushed it, giving us our first direct chemical measurements of the atmosphere. The orbiter would then spend years mapping the moons, studying the magnetic field, watching the weather, and answering questions that have been sitting open since 1986. As of the knowledge available here, NASA had been studying mission concepts and no firm launch date had been confirmed, but the scientific community's consensus was clear. Uranus is the next great destination. Now, the interior. What lies beneath those blue-green clouds is one of the more spectacular territories in the solar system, even if we can't see it directly. The structure of Uranus, as best as scientists can determine from modeling, gravitational measurements, and laboratory experiments, works something like this. There is a relatively small core of rock and ice at the center. Around that core sits a thick mantle of compressed ices, water, methane, and ammonia in that hot, dense fluid state described earlier. Above the mantle is the gaseous hydrogen-helium envelope that constitutes the visible atmosphere. The entire interior, from the core outward, is under extreme pressure that reaches millions of times Earth's atmospheric pressure at the center. Under those conditions, chemistry becomes exotic. One of the most spectacular hypotheses about Uranus's interior, one with actual experimental backing, involves diamonds. Diamonds forming and raining down through the interior. Let's look at why scientists believe this might actually happen. In the interior of Uranus, methane, which is CH4, one carbon atom bonded to 4 hydrogen atoms, is subjected to temperatures of thousands of degrees and pressures of millions of atmospheres. Under those conditions, the molecules can be broken apart. The hydrogen atoms are freed, and the carbon atoms, now separated from the hydrogen, begin bonding to each other under the enormous pressure. Carbon under extreme pressure forms diamonds. The hypothesis, which has been called diamond rain, suggests that carbon atoms in the interior of Uranus continually separate from methane, crystallize into diamonds, and then the diamonds, which are denser than the surrounding fluid, slowly sink toward the core. This would mean that right now, inside Uranus, diamonds may be falling like rain through an exotic sea of compressed chemicals. The idea sounds like science fiction, but experimental evidence backs it up. In 2017, researchers at the SLAC National Accelerator Laboratory in California used high-powered lasers to create shock waves in polystyrene, a carbon-hydrogen compound similar in composition to the methane ices in Uranus, and directly observed the formation of nanodiamonds under the resulting pressure and temperature conditions. The experiment simulated conditions similar to those found roughly 10,000 kilometers below Uranus's cloud tops. The nanodiamonds formed almost immediately when the shock wave hit. While this doesn't mean we've confirmed diamond rain inside Uranus with certainty, it strongly supports the theoretical model, and many scientists now consider it a reasonable description of what's happening in there. If diamonds do form and sink toward the core, they may actually contribute to the mystery of Uranus's missing internal heat. As diamonds descend, their motion could generate heat, a process called gravitational differentiation. But if some insulating layer is preventing that heat from reaching the atmosphere, it might explain why the surface stays so cold, even if the deep interior is generating energy. This is one of the active areas of research connecting interior models to the observable behavior of the planet. Now to one of the more memorable facts about Uranus that tends to generate reactions: what the planet smells like. In April 2018, a team of researchers, including scientists from the University of Oxford, published a study in the journal Nature Astronomy, confirming that the upper cloud layer of Uranus contains hydrogen sulfide. The data came from observations made with the Gemini North Telescope, located on Mauna Kea in Hawaii. Hydrogen sulfide is the chemical compound responsible for the smell of rotten eggs. It's what comes out of volcanoes, out of swamps, and out of decaying organic matter. It's genuinely one of the least pleasant smells most people have ever encountered. If you could somehow find yourself standing in the upper atmosphere of Uranus, which would be impossible for any number of reasons, including the absence of any solid surface, the near absolute zero temperatures, the crushing absence of breathable air, and the sheer impracticality of getting there, you would be immediately overwhelmed by the odor of rotten eggs before any of the other conditions had a chance to finish you off. The discovery confirmed something scientists had long suspected about Uranus and Neptune's atmospheres, and it contrasted with Jupiter and Saturn, where the upper cloud layers are ammonia ice rather than hydrogen sulfide. This difference in chemistry reflects the different conditions during formation in different regions of the early solar system. The discovery also had implications for understanding planetary formation, why ice giants and gas giants have different atmospheric chemistry, despite all forming from the same basic pool of material. The answer seems to lie in temperature. In the colder outer regions where Uranus and Neptune formed, hydrogen sulfide could condense and accumulate in ice grains and planetesimals, while closer to the Sun, where Jupiter and Saturn formed, it was too warm for this to happen as efficiently. Let's talk about the seasons one more time, because they deserve more than just a mention. The 97.77-degree axial tilt creates seasons on Uranus that are unlike anything else in the solar system, and are frankly difficult to fully comprehend even when you try to visualize them. A Uranian year, one full orbit around the Sun, takes about 84 Earth years. Divide that by 4 seasons, and each season lasts roughly 21 Earth years. The spring and autumn near the equinoxes are relatively mild in the Uranian sense, with the Sun moving toward or away from the poles. But the summers and winters at the poles are extreme to a degree that has no analog on Earth. Consider the North Pole of Uranus. During the northern summer, the Sun is shining directly on the North Pole, circling in the sky above it, without setting for 42 years. The North Pole receives continuous sunlight for 42 Earth years. Then, as the planet moves into the northern autumn and winter, the Sun slowly pulls away, crosses the equator, and eventually shines directly on the South Pole for the next 42 years, while the North Pole sits in unbroken darkness for those same 42 years. There is no gradual seasonal change the way we experience summer sliding into autumn on Earth. The transitions happen slowly over years, but the extremes are absolute. During the Voyager 2 flyby in January 1986, Uranus happened to be near its southern summer solstice, which meant the South Pole was pointing roughly toward the Sun and toward the incoming spacecraft. This had a practical effect on the mission, because the southern hemisphere was in continuous sunlight, while the northern hemisphere was in continuous darkness. Voyager 2's cameras could see the lit southern hemisphere well, but almost nothing of the dark northern side. The planet we photographed in 1986 was essentially showing us just half of itself. The transition through the equinox in 2007 was scientifically important because, for the first time, both hemispheres were receiving similar amounts of sunlight. As the northern hemisphere warmed up after its decades-long winter, the atmosphere became more active. Clouds formed, storms appeared. The relatively featureless disk that Voyager 2 had photographed began developing visible structure. In 2014, that activity reached a peak of sorts when Keck Observatory observers watched an extraordinary outbreak of storms across Uranus's northern hemisphere. Bright cloud features unlike anything seen since the Voyager era. The storms were enormous and extremely high in the atmosphere, indicating convection was carrying energy upward from deeper layers. The next major seasonal milestone for Uranus will be its northern summer solstice in 2028, when the North Pole will again point most directly at the Sun. If the pattern holds, and the evidence suggests it will, atmospheric activity should intensify in the years approaching that solstice and in its aftermath, as the newly warmed northern hemisphere drives weather systems we haven't seen before. One of the things that makes Uranus such a rich target for future exploration is the sheer number of questions it leaves open. The mystery of the missing internal heat, the true structure of the interior, and whether diamonds really do rain down through it. The nature of the wildly asymmetric magnetic field, and whether it wobbles in ways that affect the ring system and the moons. The geological history of Miranda, and how its astonishing cliffs and coronae came to be. Whether any of the larger moons have internal oceans of liquid water, some models suggest Titania and Oberon might, and what that might imply. Why the atmosphere was so quiet in 1986, and so active around 2014. How the rings behave over time. Are they stable? Are they gaining material from collisions among small inner moons? Are they slowly decaying? None of these questions can be answered adequately from Earth, or even from Hubble. A spacecraft that actually orbits Uranus, that lives there for years, watching the planet through a season, measuring the magnetic field in real time, dropping a probe into the atmosphere to taste the chemistry directly. That spacecraft would transform our understanding of this world from a collection of puzzling observations into something approaching a genuine picture. The Uranus Orbiter and Probe mission, if it launches in the early 2030s as the Decadal Survey recommends, would arrive at Uranus around the mid-2040s. By that point, the planet will be heading into northern autumn, and the spacecraft would be able to watch weather patterns change as the planet moves away from its 2028 solstice. It would study all 27 known moons and potentially discover more. It would map the magnetic field in enough detail to understand whether the models about the icy mantle generating it are correct. And the atmospheric probe, before it's destroyed by the pressure, would send back the most detailed direct measurements of Uranus's composition ever obtained. That mission, if it happens, will be one of the great planetary science achievements of the 21st century. It's worth stepping back for a moment and thinking about what it means that we've only visited this planet once, more than 38 years ago, and never entered orbit. The solar system is enormous, and sending spacecraft across billions of kilometers takes time. A Uranus mission requires 13 or more years of travel time with current propulsion technology. But compared to the body of knowledge we have about Mars, Jupiter, Saturn, and even Pluto from New Horizons, our knowledge of Uranus feels like a preliminary sketch. We have one flyby's worth of close-up data, supplemented by telescopic observations across the electromagnetic spectrum. And from that, we've had to construct models of a planet's interior, a planet's history, and the nature of an entire class of planetary body. The fact that we've gotten as far as we have, confirmed the diamond rain hypothesis in the lab, identified hydrogen sulfide in the clouds, found a hidden plasmoid in decades-old data, traced the history of a giant impact that tipped the planet sideways, is a testament to what patient, ingenious science can do with limited information, and it makes the prospect of a dedicated mission all the more exciting. Every answer a Uranus orbiter provides will almost certainly generate 3 new questions we didn't know to ask. Here's something else to think about. Of the 8 planets in our solar system, the gas giants and ice giants, Jupiter, Saturn, Uranus, Neptune, collectively have more mass than all the rocky planets combined, by a wide margin. And of the 4, the 2 ice giants represent a class of planet that turns out to be extremely common in the universe. When astronomers study exoplanets, planets orbiting other stars, A significant proportion of them fall into the sub-Neptune or ice giant size range. Understanding Uranus and Neptune better isn't just about understanding our own solar system. It's about understanding what kind of worlds fill the galaxy. Because worlds in the Uranus size and composition range appear to be among the most common types of planets out there. Ice giants, it turns out, may not be the exotic rarities they once seemed to be. They may be normal. It's rocky planets like Earth that are the statistical minority. Studying Uranus, then, is in some sense studying the representative planet of the galaxy, the type of world that fills most of the exoplanet catalogues. Every measurement we make of Uranus provides a data point that astronomers comparing it to exoplanets thousands of light years away can use to understand those distant worlds better. The planet that William Herschel stumbled across in a garden in Bath in 1781, the one he thought was a comet, the one that French astronomers named after him and British astronomers named after their king. This planet that rolls on its side through the darkness of deep space, smelling of rotten eggs, raining diamonds, colder than any other atmosphere in the solar system, tumbling its magnetic field through space like a wobbling gyroscope. This is the planet that may hold some of the most important clues about what the galaxy is made of. The orbital timing of Uranus is itself a story. It takes 84 Earth years to circle the Sun, so since Herschel's discovery in 1781, Uranus has only completed about 2.9 orbits. It completed its first full orbit around 1865, its second around 1949, and it won't complete its third until about 2033. In other words, in all of human history since the telescope was invented and Uranus was found, the planet has gone around the Sun less than 3 times. The slow, patient arc of its orbit carries it so far from the Sun that each year it covers less than 4.5 degrees of arc around its orbit. From Uranus, the Sun would appear as a very bright star, not the enormous disk we see from Earth, still the brightest object in the sky by far, but diminished to a point source of intense light, perhaps 360 times fainter than it appears from Earth. And yet, for all its distance and coldness and strangeness, Uranus is bound to the Sun just as surely as Earth is. It formed from the same cloud of gas and dust 4.5 billion years ago. Its core contains the same elements. The same physics governs its orbit, its weather, its chemistry. The difference is one of position and scale. How far from the warmth of the Sun you form, how much material you accumulate in the process, what happens to hit you in the violent early history of the solar system. The story of Uranus is also, in a way, a story about how much of the universe remains genuinely unknown. We tend to assume, in an era of satellite images and instant global communication, that everything out there has been mapped and measured and explained. Uranus is a reminder that one of our neighboring planets, the one right over there, third largest in our solar system, visible with the naked eye on a dark night, remains profoundly mysterious. We don't know why it doesn't radiate internal heat. We don't know the precise details of its interior. We don't know the full history of its catastrophic tilting collision. We don't know whether its moons have subsurface oceans. We have never orbited it. We have never sampled its atmosphere. This is a planet in our own solar system, and we visited it exactly once, briefly, with one spacecraft, decades ago. Everything else is inference, modeling, and the patient work of scientists watching a distant blue-green disk through telescopes and trying to understand, with the faint light that reaches us across 2 billion kilometers, what is going on inside. The Voyager 2 team, the engineers who designed the spacecraft, the scientists who planned the trajectory, the navigators who guided it across 9 years and 4 billion kilometers of space, the instrument operators who kept everything running, achieved something extraordinary when they flew past Uranus on January 24, 1986. In just a matter of hours, they converted a largely unknown planet into a partially known one, gave us our first close look at its moons and rings and magnetic field, and left behind a dataset that scientists are still extracting discoveries from 38 years later. What the next mission will find is anyone's guess. The history of solar system exploration suggests that every time we've gotten a spacecraft into close proximity with a world we thought we understood, we've been surprised. Jupiter was supposed to be a largely featureless giant. It turned out to have weather systems more violent and complex than anything on Earth. Pluto was expected to be a dead, frozen ball. New Horizons found nitrogen glaciers, towering mountains of water ice, and a heart-shaped basin visible from space. Saturn's tiny moon Enceladus was supposed to be geologically dead. Cassini found it spraying water vapor from active geysers at its south pole. Europa's ice shell was expected to be simple. It turned out to conceal a global ocean that might contain more liquid water than all of Earth's oceans combined. Uranus has given us every reason to expect that a dedicated mission will find things we haven't anticipated. The diamond rain, the rotten egg clouds, the rolling axial tilt, the tumbling magnetic field, the icy cliffs of Miranda, the dark rings, the missing heat. Each one of these is a signal that Uranus operates by rules that don't quite match anything else we've seen. And if history is any guide, the surprises a Uranus orbiter delivers will be the ones nobody predicted. The moons alone could justify the mission. 27 moons, most of them barely characterized, orbiting a tilted planet in a tilted ring system. The 5 major moons have barely been photographed. Voyager 2's images, taken during a brief flyby from tens of thousands of kilometers away, are the best we have. An orbiter would be able to image Miranda's cliffs in detail, map the surface of Titania and Oberon, look for signs of geological activity on Ariel, measure the composition of the dark material on Umbriel. Any one of those moons might hold surprises comparable to what Cassini found at Enceladus. There's also the question of what lives at Uranus that we haven't discovered yet. Not life, at least not life as we currently understand it, though the ice giants are not on the short list for biological habitability. New moons, rather, new rings, new ring shepherds, tiny moonlets whose gravity maintains the sharp edges of the rings. Voyager 2's quick flyby couldn't have found everything. Hubble has discovered additional small moons over the years, but there are almost certainly more waiting to be found by an orbiting spacecraft with better instrumentation. The rings themselves are still mysterious in their details. Why are they so dark? How long have they been there? Are they actively maintained by nearby moonlets? How does Uranus's bizarre magnetic field interact with the charged particles in the rings? What happens to the ring structure during the extreme seasons, when one hemisphere of the ring system faces the Sun and the other faces away? None of these questions can be answered from Earth. One thing worth noting is how Uranus fits into the broader history of how humans have understood their place in the universe. For thousands of years, people looked at the night sky and saw 5 wandering stars: Mercury, Venus, Mars, Jupiter, Saturn, moving against the fixed backdrop of the stars. The solar system was those 5 planets plus Earth, and that felt complete. Then in 1781, a musician with a homemade telescope in a garden in England found another one. The solar system doubled in known size overnight. Then Neptune was found in 1846. Then Pluto in 1930, later reclassified. And then, with better telescopes, dozens of moons around the outer planets, thousands of asteroids, a full belt of icy bodies beyond Neptune. The universe kept getting bigger, more complicated, and more full of things we hadn't known were there. Uranus was the first step in that expansion. It was the discovery that broke the ancient assumption that the night sky had been fully catalogued by human eyes. Everything after it, every moon, every asteroid, every distant galaxy, every exoplanet, follows in the path that William Herschel opened when he noticed that small, fuzzy object moving against the stars. And the planet at the center of that revolution in human understanding turns out to be one of the strangest, most puzzling, most fascinating objects in the solar system. It rolls on its side, it smells of rotten eggs, its interior may be raining diamonds, it keeps its heat buried. Its magnetic field tumbles through space on a journey that never quite repeats. Its moons are named after Shakespeare. Its rings are darker than coal. Its south pole basks in sunlight for 42 years, while the north drowns in darkness, and then they trade. Uranus doesn't just deserve a return mission, it demands one. The planetary science community agrees. The decadal survey said it clearly. Among all the targets available in the next decade, the Uranus Orbiter and Probe is the highest priority for a flagship mission. After 84 years, or rather, after 244 years of knowing it exists, and only one brief visit to it, science is ready to go back and actually look. In the meantime, Uranus continues its slow roll around the Sun, tilted impossibly on its side, blue-green and cold and mysterious, completing that long 84-year orbit at a pace so stately that it has only circled the Sun 3 times since the moment Herschel wrote it down in his garden journal. Its diamonds fall silently in the dark interior. Its rings reflect almost no light. Its moons orbit in their tilted plane, named after characters from plays performed 4 centuries ago. Its magnetic field corkscrews through space in a pattern that bends every expectation. This is the 7th planet from the Sun, the most bizarre world in the solar system, and one of the most compelling mysteries in all of modern science. And we've barely scratched the surface. Sources and timeframes embedded in the research section above reflect published science as of the knowledge cutoff. The decadal survey cited is the Origins, Worlds and Life, a decadal strategy for planetary science and astrobiology, 2023-2032, published April 2022 by the National Academies of Sciences, Engineering and Medicine. The hydrogen sulfide discovery was published in Nature Astronomy, April 2018. The diamond formation experiment was conducted at SLAC National Accelerator Laboratory and published in 2017. The plasmoid discovery was published in Geophysical Research Letters, 2020. Lead author, Gina DiBraccio. Expanded sections, deepening the story. There's a particular kind of awe that comes from sitting with a number long enough for it to become real. 2.87 billion kilometers. That's the average distance between Uranus and the Sun. Say it again slowly. 2.87 billion kilometers. At the speed of sound, which is roughly 1,235 kilometers per hour in Earth's atmosphere, you'd travel for about 265 years before you arrived. At the speed of a modern passenger jet cruising at around 900 kilometers per hour, the journey would take roughly 364 years. The Apollo astronauts, traveling to the Moon in about 3 days, would need something on the order of 22,000 years to reach Uranus at that speed. These numbers become almost theological in their scale. They push the brain into a territory where ordinary units of time and space stop meaning much. And yet, Uranus is our neighbor, in cosmic terms. The nearest star to the Sun, Proxima Centauri, is about 40 trillion kilometers away, more than 13,000 times farther than Uranus. The Milky Way galaxy stretches roughly 1 quintillion kilometers from edge to edge, nearly 500,000 times farther still. On those scales, Uranus is practically in our backyard, and yet most people alive today have never thought about it for more than a few minutes. It hangs in the solar system, rolling along in its sideways orbit, doing something genuinely unprecedented in all of planetary science, and most of humanity is looking at something else. Part of the reason for that neglect is visibility, or the lack of it. Uranus is technically visible to the naked eye under ideal conditions. Very dark sky, no light pollution, good eyesight, and the knowledge of exactly where to look. Its apparent magnitude, a measure of how bright it appears in the sky, ranges between about 5.3 and 5.9, depending on its distance from Earth at any given time. The human eye, under ideal conditions, can see objects down to about magnitude 6 to 6.5. So Uranus is right at the edge, possibly visible, but so faint and slow-moving that for thousands of years of human stargazing, nobody identified it as anything other than a dim, unremarkable speck. It didn't look different from a faint star. It didn't move fast enough to catch attention. It was hiding in plain sight. This is one of the quiet marvels of the Herschel discovery. The planet was observed at least 21 times before 1781 by various astronomers, Flamsteed's 1690 observation being the earliest confirmed. Each time, the observer dutifully logged a star in that position and moved on. There was nothing remarkable about a faint star. Without a telescope capable of showing its disk, there was nothing to distinguish Uranus from the thousands of other faint objects scattered across the sky. What Herschel had that the others didn't was a combination of 2 things: a superior telescope and a systematic observing method that involved comparing objects across multiple nights to detect movement. When he saw the disk and noted the slight movement, his mind was already primed to ask the question, "What is this?" rather than to file it away automatically as a star. The telescope Herschel used that night wasn't purchased from a shop. He'd built it himself. Herschel was an accomplished telescope maker, as well as an astronomer and musician, and his instruments were considered some of the best in England at the time. The mirror in his telescope was ground and polished by his own hand, to a degree of optical precision that allowed him to see what others had missed for nearly a century. There's a lesson in that about the relationship between tools and discovery. The right instrument, in the right hands, at the right moment, changed human understanding of the solar system forever. Herschel went on to have a prolific career after the Uranus discovery. He identified and catalogued thousands of double stars, pairs of stars in close proximity, often orbiting each other. He made fundamental contributions to understanding the structure of the Milky Way, correctly deducing that the Sun sits inside a disc-shaped collection of stars, but incorrectly placing it near the center. The actual center of the Milky Way is tens of thousands of light-years away from the Sun. He built telescopes of increasing size, including one with a primary mirror 1.2 meters across, the largest in the world at the time, that he assembled in his garden at Slough. And in 1787, 6 years after discovering Uranus, he turned his telescope to the new planet and found 2 of its moons, Titania and Oberon, which he named after characters from A Midsummer Night's Dream, establishing the Shakespearean tradition that all subsequent Uranian moons would follow. His sister Caroline Herschel worked alongside him throughout much of his career, grinding mirrors, recording observations, assisting in systematic surveys, and became in her own right one of the most accomplished astronomers of the era, discovering 8 comets and earning gold medals from the Royal Astronomical Society. The Herschel household was, in a sense, the most productive astronomy operation in England during the late 18th century. William Herschel died in 1822 at the age of 83. He had lived long enough to see his discovery of Uranus cement his reputation as the greatest observational astronomer of his generation, and to see the name Uranus, proposed by Bode, begin gaining traction internationally, though the final universally accepted adoption of that name came only after Herschel's death. His son John Herschel continued his father's work and extended the survey of the southern sky from the Cape of Good Hope in South Africa during the 1830s. The Herschel family's contribution to astronomy spans generations and constitutes one of the more remarkable family legacies in the history of science. Understanding the context of the 1986 Voyager 2 encounter requires knowing a bit more about the spacecraft itself and the extraordinary precision of the trajectory that got it there. Voyager 2 had already flown past Jupiter in July 1979, nearly 4 years before Uranus, and past Saturn in August 1981, gaining velocity from each planet's gravity like a ball ricocheting off walls. By the time it reached Uranus, it had been traveling for 8.5 years and had crossed more than 2 billion kilometers of deep space. Its nuclear power source, radioisotope thermoelectric generators, or RTGs, converting the heat from decaying plutonium-238 into electricity, had been providing power through all of that time. The communications antenna, 3.7 meters across, had to aim itself at Earth with extraordinary precision from an enormous distance, because even a small misalignment at that range would cause the signal to miss entirely. The encounter itself, on January 24, 1986, was planned and executed with a precision that still impresses engineers today. The spacecraft had to thread between the narrow gaps in Uranus's ring system at the right speed and angle to both avoid damage and set up the correct trajectory onward to Neptune, all while its instruments were taking thousands of measurements and images. The communications delay at Uranus's distance, the time for a signal to travel from Earth to Voyager 2 and back, was about 2 hours and 40 minutes each way, meaning the team on Earth couldn't intervene in real time if something went wrong. The spacecraft had to operate autonomously, executing a precisely pre-programmed sequence, and it had to do so perfectly. It worked. The flyby was a textbook success. The 10 new moons were discovered, the 2 new rings confirmed, Miranda's impossible terrain photographed, the magnetic field mapped. But one thing worth noting is how brief the actual closest approach window was, the period during which Uranus completely filled the imaging camera's field of view and the highest resolution images could be taken. The geometry of a flyby means that the spacecraft approaches the planet at high speed, reaches closest approach in a matter of hours or even minutes for the highest resolution window, and then recedes. The images of each moon, the closest looks at the rings, the magnetometer readings at minimum distance, all of it was compressed into a period of hours. For Uranus, one of the major moons, Miranda, was at the right distance for a close approach, which is why we have such spectacular, if low resolution by modern standards, images of its cliffs. The other moons were observed from greater distances. If you've ever wondered why the Voyager 2 images of Uranus look somewhat blurry and low detail compared to the extraordinary images from, say, the Cassini mission at Saturn, this is why. Cassini spent 13 years in orbit around Saturn, circling hundreds of times, taking millions of images at various distances and geometries. Voyager 2 had hours at Uranus. The comparison is deeply unfair, and yet it reveals exactly the difference between a flyby and an orbiter. An orbiter has time. A flyby has one chance. The rings of Uranus, dark as they are, have a complex and fascinating structure that took decades to piece together from observations. The initial discovery in 1977 identified 9 rings, and the Voyager 2 flyby added 2 more to bring the total to 11 at the time. Hubble observations in 2005 pushed that to 13, and the full set continues to be studied. What makes the ring system particularly interesting from a dynamics standpoint is the role played by shepherd moons, small moonlets whose gravity acts to confine ring material into narrow bands. The best-known example in the solar system is the ring shepherd system in Saturn's F ring, where 2 small moons, Prometheus and Pandora, orbit on either side of the ring and keep it tightly confined. Uranus has similar shepherds. The 2 small moons Cordelia and Ophelia orbit on either side of the Epsilon ring and keep it from spreading out. These moons were discovered by Voyager 2 in 1986 and are named, appropriately for Uranus, after characters from Shakespeare's Hamlet. The Epsilon ring is about 60 to 100 kilometers wide at various points, but its internal structure is uneven, wider where the ring material crowds together and narrower in other sections, influenced by the gravitational pull of Cordelia and Ophelia. The ring is also eccentric. It doesn't follow a perfectly circular orbit, but instead is slightly elliptical, with the ring material organized along this ellipse in a way that seems to defy simple physical expectations. The mechanism that maintains a narrow, eccentric ring over millions of years is still not completely understood. The other inner rings, alpha, beta, eta, gamma, delta, are even narrower, some only a few kilometers wide, and each has its own distinct characteristics. The gamma ring, for example, is very narrow and very bright relative to the others. The eta ring has a faint, broad component on one side and a narrow, bright component on the other. The lambda ring, one of the faintest, sits just inside the epsilon ring and is almost invisible. The 2 outer rings, mu and nu, discovered by Hubble in 2005, are broader and more diffuse, extending thousands of kilometers in width. Mu, in particular, has a faint blue color compared to the otherwise uniformly dark inner rings, an unusual observation that may indicate the Mu ring is composed of dust-sized particles that scatter blue light preferentially, similar to the way Earth's atmosphere scatters blue light to give us a blue sky. The source of material for these outer rings is thought to be impacts on small inner moons, which kick up dust and debris that spreads into rings. Collectively, the ring system of Uranus spans from roughly 38,000 kilometers above the planet's cloud tops out to roughly 98,000 kilometers, with the widest gap between the inner and outer ring groups. All of the rings orbit in the same tilted plane as the moons, aligned with Uranus's equator. Seen from above the solar system, the ring system looks almost like a target drawn around a sideways planet, circular rings surrounding a world that orbits face-on to the Sun for most of each 84-year year. The history of how Neptune's discovery followed from Uranus's is one of the great stories in the history of science, and it's directly connected to the strangeness of Uranus's orbit. After Herschel discovered Uranus in 1781, and astronomers began tracking it carefully, something became apparent over the following decades. Uranus wasn't quite where it should be. Based on Newtonian mechanics and the gravitational influence of all the known planets, Uranus should have followed a predictable path around the Sun. It didn't. Its orbit had small but detectable deviations from the predicted path, what astronomers called irregularities. 2 possible explanations existed. Either Newton's laws broke down at the scale of Uranus's orbit, or there was another large body out there, not yet discovered, whose gravity was tugging Uranus off its predicted course. 2 mathematicians, working independently and simultaneously, chose to assume Newton's laws were correct and worked backward from the orbital irregularities to calculate where an unknown planet would have to be in order to produce them. John Couch Adams in England and Urbain Le Verrier in France both completed this calculation within months of each other in 1845 and 1846. Le Verrier's prediction reached the Berlin Observatory, where astronomer Johann Gottfried Galle pointed a telescope at the predicted location on September 23, 1846, and found Neptune, within 1 degree of where Le Verrier had calculated. Adams had made a similar prediction, but had been unable to get British astronomers to search systematically enough, quickly enough, to claim the discovery. The discovery of Neptune is one of the most celebrated examples of theoretical prediction in science. Mathematics pointing to a planet that no human eye had recognized, and then the telescope confirming it. And the whole chain of reasoning began with the strange behavior of Uranus, the planet Herschel had stumbled across in 1781, without any mathematical prediction at all. The two ice giants are thus linked in history as well as in physics. Neptune and Uranus are siblings in a deep sense, similar in size, similar in composition, both tilted more than most planets, though Neptune's 28-degree tilt is nowhere near as extreme as Uranus's. Both blue-green from methane, both suspected of diamond rain, both generating unusual magnetic fields. They formed in the same outer region of the proto-solar disk, though models of exactly how and where are still debated. Some theories suggest they formed closer to the Sun and were later scattered outward by gravitational interactions with Jupiter and Saturn. The Nice model, named for the city in France where the group of researchers worked, is one influential framework that describes the early evolution of the solar system as a violent period of gravitational reshuffling, during which Jupiter and Saturn moved through certain orbital resonances and kicked Uranus and Neptune outward to their current orbits, while sending a rain of debris inward to bombard the inner solar system, a period called the Late Heavy Bombardment, thought to have occurred around 4 to 3.9 billion years ago. Whether the tilting of Uranus happened before, during, or after this orbital migration is one of the more active areas of theoretical research in planetary formation. The question of Uranus's internal structure, what's actually in there, is one that scientists approach through a combination of techniques, because we can't send a probe to the interior of an ice giant the way we drill for oil or take geological samples. The tools available are gravitational measurements, seismic analogy, though Uranus doesn't have seismometers on it, modeling of known physics under extreme conditions, and laboratory experiments like the Slack Diamond experiment that simulate those conditions in miniature. The basic layered model, rocky core, icy mantle, gaseous envelope, is well established, but the details are enormously uncertain. The size of the core, the exact composition of the mantle, whether the transition from mantle to gas envelope is a sharp boundary or a gradual continuum, all of these are open questions. Some models suggest Uranus might not have a distinct core at all, but rather a gradual increase in density and heavier elements from the outer atmosphere all the way to the center. Other models suggest a relatively compact rock iron core of perhaps 1 to 3 Earth masses, surrounded by a vast mantle. The ices in the mantle, water, methane, ammonia, behave in exotic ways under pressure. At the temperatures and pressures in the upper mantle, they're a supercritical fluid, meaning they're past the point where liquid and gas phases have distinct identities. Deeper still, they may become what physicists call superionic ice, a state of matter where the oxygen atoms of water molecules lock into a crystal lattice, while the hydrogen ions flow freely through the lattice like a liquid. This creates a material that is simultaneously solid in one respect and liquid in another, conducts electricity readily, and behaves in ways that have no parallel in everyday experience. The existence of superionic water ice has been demonstrated in laboratory experiments, and it's thought to exist in the deep interiors of both Uranus and Neptune. This superionic layer, if it exists, is likely connected to the unusual magnetic fields of both ice giants. The freely flowing hydrogen ions in the superionic water create a layer that can act as a dynamo, generating a magnetic field through the movement of electrically conducting fluid, just as Earth's liquid outer core generates our magnetic field through the flow of molten iron. But because this layer is positioned partway through the planet rather than at the center, the resulting magnetic field has the off-center, tilted character that observations reveal. The geometry of the generating layer determines the geometry of the field, and in Uranus's case, the geometry is strange. One of the more exotic proposals for what might happen in the deepest parts of the ice giant mantle involves what happens to water at extreme pressure. Some theoretical work suggests that under sufficient pressure, potentially achievable in Uranus's deep interior, water molecules might dissociate into their component oxygen and hydrogen, with the oxygen atoms forming a metallic oxygen lattice and the hydrogen atoms becoming mobile protons. This plasma water state, if it exists, would have dramatically different properties from any form of water we recognize. Whether this actually occurs inside Uranus is unknown. It's one of many possibilities in a region of planetary physics where even the theoretical models are uncertain. The weather and atmospheric dynamics of Uranus deserve more than a passing mention, partly because they've changed so dramatically between what we observed in 1986 and what we see today. When Voyager 2 flew by in January 1986, the planet's south pole was facing the Sun, pointing directly at the Sun actually, given the 97.77-degree tilt, and had been doing so for roughly 2 decades at that point. The southern hemisphere was bathed in constant sunlight. The northern hemisphere was in complete darkness, and the atmosphere, at least in the images Voyager 2 sent back, appeared almost completely featureless. The blue-green disk was smooth, the clouds practically invisible against the haze, the banding that characterizes Jupiter or Saturn nowhere to be seen. This was interpreted at the time as possibly indicating a genuinely quiet, stable atmosphere, perhaps evidence of the suppressed convection that might explain the missing internal heat. If heat couldn't easily rise from the interior, maybe the atmosphere was just still. That interpretation needed revision. As decades passed and Uranus moved toward its equinox in 2007, observers with the Hubble Space Telescope and large ground-based observatories began seeing more and more activity. Clouds appeared. Banding became visible. The atmosphere, it turned out, wasn't quiet by nature. It was quiet because of where the planet happened to be in its long seasonal cycle when Voyager 2 flew past. Now, with both hemispheres receiving similar sunlight for the first time in decades, convection in the atmosphere was picking up. The 2014 storm outbreak at Keck Observatory was particularly striking. 8 large storm systems, visible in infrared wavelengths that can pierce through the upper haze, appeared in rapid succession across the northern hemisphere. The brightest of these storms reflected as much light as any cloud feature observed on Uranus since the Voyager era. Each individual storm was enormous by Earth standards. They occurred at high altitudes, higher in the atmosphere than typical cloud features, which told scientists that whatever was driving them was powerful enough to pump air from deep in the atmosphere upward through many kilometers of the lower atmosphere before emerging as visible features at high altitude. Why 2014? The season argument suggests that as the northern hemisphere moves more directly toward the Sun after decades of darkness, the new energy input drives convection that hadn't been possible during the long polar winter. But 2014 was still years before the northern summer solstice, which doesn't arrive until 2028. The timing suggests that the seasonal response is complex and nonlinear, not simply a matter of the hemisphere faces the Sun, therefore it gets stormy. Predicting what Uranus's weather will do between now and the 2028 solstice, and then in the decades after, is one of the key scientific goals of the proposed Uranus Orbiter and Probe mission. A spacecraft in orbit would be able to watch the atmospheric evolution in real time, correlating cloud activity with seasonal position, measuring the vertical structure of the atmosphere with the probe, and building a model of Uranian weather that could then be applied to ice giants around other stars. One of the things worth dwelling on is the experience of existing at Uranus, not as a visitor, which is impossible, but in imagination, because the imagination is the only vehicle we have right now. Stand notionally at some point in the outer atmosphere of Uranus, in the layers where the hydrogen and helium and methane blend together in cold, sluggish currents. Around you is a sky the color of deep ocean water, cyan above, shading to blue below, without horizon or ground, just an endless gradation of atmosphere in every direction. The Sun, far behind and above, is visible as an intensely bright star, brighter than anything else in the sky, casting pale blue-tinted light through the methane haze, but small, tiny. It would appear roughly 400 times smaller in diameter than it does from Earth. The wind moves around you at hundreds of kilometers per hour, but there's nothing to measure that against. no landscape to blur past, just the slow churn of colored clouds at the same altitude and empty haze below. The temperature around you is around -220 degrees Celsius. The pressure is slightly above what we experience as 1 atmosphere at sea level on Earth. This is the region where the atmospheric pressure roughly equals what you'd feel at the surface of an ocean on land. Deeper, the pressure rises rapidly, and within a few hundred kilometers, it becomes too great for any material we could construct to survive. The smell, hydrogen sulfide from the upper cloud layer, would be overwhelming and immediately nauseating if there were any air for your olfactory system to process, but of course there isn't, because you couldn't breathe the hydrogen-helium mix even if the temperature weren't lethal and the pressure weren't killing you. There's no day or night in the conventional sense. You're too deep in the atmosphere for the rotation to produce alternating light and dark in the usual way, and depending on where Uranus is in its orbit, either a polar hemisphere or the equatorial region might be pointed toward that distant, bright star. If you're in the southern hemisphere during southern summer, the sun circles in the sky above you without setting, dimming and brightening somewhat with the planet's 17-hour rotation, but never disappearing below any horizon. The 17-hour day means that a local day passes in the time it takes to work a shift and sleep a few hours. The rings, if you could somehow see through the atmosphere and the haze to look outward, would be nearly invisible. Dark rings around a dark sky. The moons, so far overhead in their orbits, would be tiny points of light. Miranda might be discernible as a slightly larger disk if you knew where to look, but Titania and Oberon, at their distances, would be just bright stars. It's a world that, in every respect, operates entirely outside the range of human evolutionary experience. Our brains built to understand a warm, oxygenated, medium gravity, medium temperature environment on a world with a modest axial tilt and a 24-hour day. Uranus offers none of those anchors. The naming of Uranus's moons is worth exploring in more depth, because the tradition is genuinely unusual in the context of solar system nomenclature and reflects something interesting about the history of planetary science. When Herschel found Titania and Oberon in 1787, he chose names from Shakespeare's A Midsummer Night's Dream, Titania being the queen of the fairies and Oberon her consort. At the time, this was an idiosyncratic personal choice, rather than the founding of an official tradition. Subsequent moons found by other astronomers continued the pattern, sometimes choosing Shakespeare, sometimes Pope. William Herschel, the English brewer and amateur astronomer who discovered Ariel and Umbriel in 1851, chose names from Alexander Pope's poem The Rape of the Lock, Ariel being a sylph in that poem and Umbriel a gnome. The names also appear in Shakespeare's The Tempest, and that dual literary connection has been embraced. Miranda, found by Gerard Kuiper in 1948, is named for the character in The Tempest, the daughter of the magician Prospero. When Voyager 2 discovered 10 new small inner moons in 1986, the naming team chose characters from across Shakespeare: Cordelia from King Lear, Ophelia from Hamlet, Bianca from The Taming of the Shrew, Cressida from Troilus and Cressida, Desdemona from Othello, Juliet from Romeo and Juliet, Portia from The Merchant of Venice, Rosalind from As You Like It, Puck from A Midsummer Night's Dream, and Belinda from Pope's Rape of the Lock. The 11 known moons at the time thus spanned Shakespeare's comedies, tragedies, and romances. The smaller irregular moons found in subsequent years by Earth-based surveys added more names: Caliban, the monstrous creature from The Tempest, and Sycorax, Caliban's mother, in the same play, for 2 irregular retrograde moons discovered in 1997. Prospero, the magician from The Tempest, for one discovered in 1999. Setebos, a deity mentioned in The Tempest, for another. Stefano and Trinculo, the drunken butler and jester from The Tempest, for 2 more. The moon Ferdinand, a Perdita, Margaret, Mab, Cupid, and others that followed continued the tradition. The effect is that the Uranian system has a distinctly literary quality that no other planetary system shares. When astronomers talk about the moons of Jupiter, they talk about Io and Europa and Callisto and Ganymede, ancient myths, figures of the divine. When they talk about Saturn's moons, they invoke Titan and Enceladus and Rhea, giants and monsters from Greek mythology. But the moons of Uranus are Hamlet's lover, Lear's faithful daughter, Prospero's monstrous slave, Shakespeare's fairy queen. The entire system is populated by characters from the human literary imagination, and there's something fitting about that, given that Uranus itself was found not through mathematical prediction or divine revelation, but by a musician standing in a garden on a cold English night, pointing a telescope at the sky out of pure curiosity. The Voyager 2 spacecraft, now traveling through interstellar space, crossed a boundary called the heliopause, the outer edge of the bubble of solar wind that the sun blows outward in all directions, around November 2018. This made it the second human-made object to enter interstellar space, after Voyager 1, which crossed the heliopause in 2012. 5 objects have now left, or are on trajectories that will eventually take them out of, the solar system: Voyager 1, Voyager 2, and the 3 Pioneer and New Horizons spacecraft, though the latter 2 are still within the heliosphere as of available knowledge. Voyager 2 carries a golden record, a 12-inch gold-plated copper disc containing sounds and images from Earth, intended as a greeting to any intelligent civilization that might intercept the spacecraft millions of years from now. The record includes greetings in 55 languages, music from around the world, sounds of nature, and images of Earth and its life. The decision to include this record was made by Carl Sagan and a team of collaborators. Whether Voyager 2 will ever be found by any intelligence other than our own is entirely unknowable. But the fact that the one spacecraft we sent to Uranus is now in the space between stars, carrying a compressed portrait of human civilization, adds a particular resonance to the story. Voyager 2 continues to communicate with Earth via NASA's Deep Space Network, though its signal, transmitted at a power comparable to a refrigerator light bulb, takes well over 18 hours to travel from Voyager 2's current position back to Earth. By the time this script was written, Voyager 2 was more than 20 billion kilometers from the Sun. It is traveling at about 15.4 kilometers per second relative to the Sun. Even at that speed, it would take Voyager 2 about 40,000 years to reach the nearest star system if it were headed in that direction, which it isn't. There is a version of the future where, sometime in the 2040s, a spacecraft enters orbit around Uranus, and for the first time in history, human instruments circle the most bizarre planet in the solar system. This spacecraft, whatever name it eventually carries, would spend years watching the planet through its seasons, mapping its moons, measuring its magnetic field in continuous detail, watching its weather evolve as the northern hemisphere moves through the post-solstice period. The atmospheric probe would descend through the layers of the atmosphere, transmitting data for as long as it survived. It would measure the actual abundances of hydrogen, helium, methane, hydrogen sulfide, water vapor, ammonia, and other compounds directly rather than inferring them from telescopic observations. It would sample the wind speeds and temperatures at different pressure levels. It might confirm or challenge the models of atmospheric structure that have been built from Voyager 2's data and Hubble observations. And then, at some depth below where we can see from space, the pressure would crush it and it would go silent. But those final transmissions, squirted up through the atmosphere and relayed by the waiting orbiter, would carry the most direct measurements of Uranus's interior we've ever had. The orbiter, meanwhile, would circle Uranus and its moons for 4 or more years, potentially the prime mission period, before budget realities or hardware failures end it. It would encounter Miranda dozens of times and image those cliffs in extraordinary detail. It would map the composition of Ariel's bright terrain and find out why it looks so fresh. It would study Umbriel's dark surface in detail and possibly identify what's coating it. It would look for cryovolcanism, ice volcanoes erupting with water or ammonia, on any of the moons where internal heat might still be active. It would study the rings in detail, watching how the material moves and how the shepherd moons maintain the ring boundaries. And it would do all of this from a platform that, unlike Voyager 2's brief flyby, has the luxury of time. Time to watch seasonal changes. Time to image the same feature from different angles and distances. Time to build up statistical records of magnetic field variations and weather patterns. Time to do science, rather than just grab as much data as possible in a single frantic pass. The scientists who build that mission and the engineers who fly it are almost certainly alive right now. Some of them may be students in universities studying planetary science or aerospace engineering. Some of them may be early career researchers at NASA or ESA, or collaborating institutions around the world. They will spend decades building toward this mission, and many of them will be in the later years of their careers, or retired, or gone, when the spacecraft finally arrives. The 13-year travel time means that a researcher who pours their professional life into designing an instrument for the Uranus orbiter may not live to see the science it returns. That's the kind of long-view commitment that planetary science demands, and the kind that the best scientists in the field make without hesitation, because the science matters even if the individual doesn't get to see all of it. Let's think about what a 97-degree axial tilt actually looks like from outside the solar system. If you were an alien astronomer studying our system from the direction of, say, Alpha Centauri, you would see the Sun at the center, orbited by 8 planets at various distances. Most of them would appear to rotate in a reasonably upright fashion, tilted from a degree or two to about 27 degrees, spinning tops more or less perpendicular to their orbital planes. Earth would look like a ball spinning with its axis tilted about 23 degrees off vertical. Saturn would look similar, with its remarkable ring system orbiting in the equatorial plane of a planet tilted at about 27 degrees. And then there would be Uranus. From a direction perpendicular to Uranus's orbital plane, it would look like a ball rolling sideways, axis nearly horizontal, rotating so that what we'd call north pointed sideways rather than up. Its rings, aligned with its equator, would appear as rings orbiting around a planet's equator, but the equator would be tipped nearly 90 degrees, so the rings would appear nearly edge-on from some angles and face-on from others as Uranus moved through its orbit. At solstice, one pole of Uranus would point almost directly toward the Sun, and the planet would appear to be a sphere, with the sunlit hemisphere entirely on one side. The dark hemisphere would be the other half, facing away from the Sun. In the orbital direction the planet came from, the previously sunlit hemisphere would be visible. Ahead, the hemisphere that had just emerged from 42 years of darkness. Nothing else in the solar system looks quite like this. Venus is tilted so extremely, 177 degrees, that it rotates backward, but its axial tilt is so close to 180 degrees that it appears almost upright relative to the orbital plane, just upside down. Uranus is the one planet that genuinely orbits on its side, and from outside, that's immediately obvious and immediately unlike anything else. If that alien astronomer were cataloging our solar system in a survey of exoplanets, they would note Uranus's tilt as a significant outlier, and they would be right. Among all the planets studied by exoplanet surveys, extreme axial tilts are seen, but not commonly. What the existence of Uranus tells us is that giant impacts of the kind that can tip an entire planet onto its side were possible, perhaps common, during the early violent period of solar system formation. Other star systems may have their own sideways rolling Uranuses, invisible to us for now but statistically expected. The alien astronomer's catalogue might have a whole category for it. In the years and decades ahead, before any dedicated spacecraft arrives at Uranus, ground-based and space-based telescopes will continue to monitor the planet. The James Webb Space Telescope, launched in December 2021 and now operating at its observing position roughly 1.5 million kilometers from Earth, has the infrared sensitivity and resolution to observe Uranus and its moons in ways not previously possible. Webb has already imaged Uranus in the infrared, capturing ring structures and moons with extraordinary clarity. Future observations will track atmospheric changes as the 2028 solstice approaches. Watch the rings for dynamic changes and search for any signs of activity on the major moons. The power of Webb for Uranus science lies in its infrared capabilities. The planet's cold atmosphere emits most of its energy in infrared wavelengths, and Webb can detect that emission with a sensitivity far beyond previous telescopes. By mapping temperature variations across the disk of Uranus in the infrared, scientists can see into the atmosphere at different depths and track how heat is distributed, which bears directly on the mystery of the missing internal heat. If Webb can build up a detailed map of Uranus's thermal emission over months and years, the patterns might reveal the mechanism that keeps the interior heat from reaching the surface. The rings, which are extremely dark in visible light, are more readily visible in certain infrared bands because the ring particles emit thermally. Webb images have already shown the rings clearly, and future observations tracking how ring brightness and structure changes over years will contribute to understanding their composition and dynamics. There's a philosophical dimension to all of this that deserves a moment of consideration. We have been visiting the solar system with spacecraft for about 65 years now, and in that time, we've learned that every world is strange in its own way. The Moon has permanently shadowed craters containing ancient ice. Mars has the largest volcano in the solar system and a canyon that would span the continental United States. Venus is a pressure cooker hell of sulfuric acid rain and crushing atmosphere, despite being about the same size as Earth. Io erupts with silicate lava in plumes that reach 500 kilometers into space. Europa's ice shell hides a global ocean. Titan has lakes and rivers and rain, but made of liquid methane instead of water. Enceladus shoots water vapor from its south pole. Pluto has a heart. Every single world that humans have looked at closely has turned out to be more interesting, more active, and more surprising than expected. Uranus, despite the one brief visit, has already joined that club. The axial tilt alone would qualify it. The diamond rain hypothesis deepens it. The rotten egg clouds and the tumbling magnetic field, and the impossible cliffs of Miranda, and the missing heat, and the dark rings darker than coal. Each of these individually would be enough to make Uranus interesting. Together, they make it arguably the most bewildering single object in the solar system. And here's the thing that makes all of this feel particularly exciting, rather than merely curious. We are almost certainly at the beginning of our understanding of this planet, not somewhere in the middle. The Voyager 2 flyby, as remarkable as it was, scratched the surface. Everything we've learned since 1986, from Hubble, from Keck, from theoretical modeling, from laboratory experiments, has added to the picture without completing it. The questions that remain open are more fundamental than the ones that have been answered. What is the deep interior actually like? Does diamond rain actually occur? Why does the planet radiate no internal heat? What created Miranda's terrain? Do any of the larger moons have subsurface oceans? What is the dark material coating Umbriel? How does the magnetosphere interact with the rings over time? What will the weather look like at the 2028 solstice and beyond? None of these questions have answers yet. Every one of them might be answered by a spacecraft in orbit around Uranus in the 2040s. The most bizarre planet in the solar system is also, in many respects, the least explored, and that will change. The planetary science community has made it their highest priority. The trajectory windows are known. The mission concept is being studied. Somewhere in the next 20 years, a spacecraft will leave Earth and begin the long journey outward, and roughly 13 years after that, it will slow down and enter orbit, and Uranus will stop being the planet we half know from one flyby decades ago. That day will be remarkable. Everything we know now about this sideways, rotten egg-smelling, diamond-raining, cold atmospheric, magnetically bizarre, Shakespearean moon-possessing, ring-wearing, slowly rolling world will be the foundation for what we learn then. And what we learn then will almost certainly be stranger than anything we've imagined. Closing deepening, the full picture. Let's revisit what we know about the composition of Uranus one more time, because the chemistry is genuinely extraordinary, and it connects to nearly everything else about the planet. At the outermost layers, you have the hydrogen, helium, methane atmosphere that gives Uranus its color and where all the weather we can observe is happening. The methane is crucial. At roughly 2.3% of the atmosphere, it's a small component by mass, but its optical properties dominate the visual appearance entirely. Methane preferentially absorbs wavelengths of light toward the red end of the spectrum, wavelengths between roughly 600 and 700 nanometers, which is the orange-red-yellow range of visible light. By absorbing red light and allowing blue and green wavelengths to reflect back, methane gives Uranus that characteristic cyan color. Neptune, which has slightly more methane, appears a deeper, more vivid blue. Below the methane layer, the atmosphere contains clouds of different compositions at different pressure levels. At the top, methane ice crystals form a haze. Deeper, at higher pressures and slightly warmer temperatures, hydrogen sulfide condenses, confirmed by the 2018 Nature Astronomy study, producing the rotten egg clouds that, if somehow experienced, would be memorably unpleasant. Deeper still, where temperatures climb to hundreds of degrees Kelvin, despite the overall coldness, water clouds may exist, and possibly ammonia clouds as well. The lack of ammonia in the upper atmosphere of Uranus is one of the clues that led scientists to suspect hydrogen sulfide was the relevant compound. On Jupiter and Saturn, ammonia freezes and forms the white clouds we see in their banded atmospheres. On Uranus, no such ammonia clouds are detected in the upper atmosphere. The explanation is that hydrogen sulfide and ammonia react with each other. They combine chemically to form ammonium hydrosulfide, which removes both from the upper atmosphere. If there's more hydrogen sulfide than ammonia, the excess hydrogen sulfide after the reaction is complete can rise to the upper layers and form the clouds detected by the Gemini telescope in 2018. The presence of hydrogen sulfide clouds implies an excess of sulfur over nitrogen in the deep atmosphere, which reflects something about where Uranus formed in the early solar system, the composition of the ice and gas grains it accreted. This chemistry carries forward into planetary formation theory in a way that's important. The different atmospheric compositions of the ice giants versus the gas giants are a record of the conditions in different regions of the protosolar disk 4.5 billion years ago. Jupiter and Saturn formed in the warmer inner region of the outer solar system, where the temperature was high enough that volatile sulfur compounds tended not to condense efficiently into ice grains. Uranus and Neptune formed farther out, in colder conditions, where these compounds could condense and be accreted into the forming planets. The rotten egg smell of Uranus is, in a sense, a fossil chemical record of where in the solar system it was born. The same logic applies to the water in Uranus's interior. Water ice was abundant in the cold outer regions of the protosolar disk, and the planetesimals that built Uranus contained large amounts of it. As these objects collided and merged under their mutual gravity over millions of years, the water ended up deep in the interior, compressed to those exotic ionic and superionic states. The planet we see today is in some sense a frozen-in-time snapshot of the chemistry and physics of the outer solar system in its earliest period, preserved in compressed and modified form. The scale of Uranian moons relative to each other is worth visualizing carefully, because the range is enormous. At the large end, Titania is about 1,578 kilometers in diameter, not as large as Earth's moon, 3,474 kilometers, but substantial. Oberon, at 1,523 kilometers, is close behind. Ariel, at about 1,158 kilometers, and Umbriel, at about 1,170 kilometers, are somewhat smaller but still geologically complex worlds. Then Miranda drops to just 472 kilometers, which sounds small but is still large enough to have its own distinctive geology and gravitational field. Below the 5 major moons, the smaller inner moons, Puck, Portia, Juliet, Cressida, Desdemona, Rosalind, Belinda, Bianca, Ophelia, Cordelia, and others, range from about 162 kilometers in diameter, Puck, the largest of this group, down to less than 20 kilometers. These small bodies are thought to be relatively dense and dark, probably similar in composition to the ring material, and several of them play direct roles in shaping and confining the rings. Cordelia and Ophelia, at about 40 and 43 kilometers respectively, serve as the shepherd moons for the Epsilon ring. The outer irregular moons, Caliban, Sycorax, Prospero, Setebos, Stefano, Trinculo, Francisca, Margaret, Ferdinand, Caliban, and others, are all small and dark, typically 10 to 200 kilometers in diameter, orbiting at large distances from Uranus, in orbits that are inclined at various angles, many of them retrograde. These are almost certainly captured objects from the outer solar system, bodies that formed somewhere else and were caught by Uranus's gravity when they passed too close. Their surface compositions may be different from the regular inner moons, potentially reflecting the composition of trans-Neptunian objects or other distant solar system populations. The discovery history of these irregular moons mostly occurred in a burst of observations between 1997 and 2003, when large ground-based telescopes with increasingly powerful detectors could identify the faint reflections from these small, dark bodies. Additional small moons are expected to be found by a future orbiter. The Voyager 2 flyby could only find moons down to a certain size, and Hubble observations have limits imposed by Uranus's distance and the faintness of small moons against the planet's glow. The question of whether any Uranian moons have subsurface oceans is one that has grown in scientific importance as our understanding of icy moon geology has developed. The discovery of Europa's ocean in the 1990s and 2000s, Enceladus's active geysers in 2005, and evidence for subsurface water on Ganymede and other moons transformed our thinking about where liquid water might exist in the solar system. The outer solar system, far from the sun's warmth, can still host liquid water if moons have sufficient internal heat, from radiogenic decay of rocky material, from tidal heating caused by gravitational interaction with their parent planet, or from the residual heat of formation. For the Uranian moons, the situation is uncertain. Thermal models of Titania and Oberon, the two largest, suggest that their interiors have cooled significantly over the age of the solar system, but may retain enough residual heat from radiogenic decay to maintain liquid water oceans at the interface between the rocky core and the outer ice shell. Whether those oceans, if they exist, are still present today or have frozen over is not known. Ariel, which shows the most geologically recent surface of the major moons, may have had cryovolcanic activity, eruptions of water or briny liquids, more recently than the others, suggesting it may have retained more internal heat. An orbiting spacecraft at Uranus could investigate these questions by studying the gravitational fields of the moons in detail. A moon with a liquid ocean layer has a different moment of inertia than a completely frozen moon of the same size, and this shows up in the way the moon's gravity affects an orbiting spacecraft. By precisely measuring the spacecraft's trajectory during close flybys of each major moon, scientists could determine whether the interior mass distribution is consistent with a liquid layer. Magnetic field measurements could also reveal whether any moon has an induced magnetic field, generated in a conductive, salty water ocean by Uranus's changing magnetic field, as Europa and Ganymede are known to have. If any of the Uranian moons turn out to have subsurface oceans, the implications for the search for habitability in the outer solar system expand considerably. We would then have another star system's worth of icy worlds to consider, alongside Europa and Enceladus, as potential environments where the conditions for life as we understand it might exist. That's a large if, and the science to establish it definitively doesn't exist yet, but the Uranus Orbiter mission would be able to address it directly. When the Planetary Science Decadal Survey published its 2022 recommendations and placed the Uranus Orbiter and Probe at the top of the flagship mission priority list, it was the culmination of years of scientific discussion and community consensus building. The decadal survey process involves hundreds of scientists submitting white papers, proposing missions, arguing their merits, and ultimately voting through a committee process to establish what the community believes should be prioritized. The result has enormous influence on NASA's budget requests to Congress and on the direction of the planetary science program for the following decade. The previous decadal survey, covering 2013 to 2022, had prioritized the Mars 2020 rover, which became Perseverance, and a Europa Clipper mission, which launched in October 2024. The time before that had focused on Curiosity at Mars and the Cassini mission at Saturn. Each decade, the community reassesses its priorities based on what has been learned, what technology has matured, and what questions have grown in scientific urgency. The case for Uranus in the 2022 survey rested on several converging arguments. The ice giant class of planet is the most common size category in exoplanet surveys, but the least studied among solar system objects. Understanding Uranus and Neptune is essential to interpreting the growing catalogue of ice giant exoplanets. The scientific questions at Uranus, the missing heat, the tilted magnetic field, the mysterious moons, the extreme seasons, are fundamental questions about planetary formation and evolution, not just curiosity about a particular planet. The technology to conduct such a mission exists or is within reach, unlike more speculative concepts. And the launch window in the early 2030s, using a Jupiter gravity assist, provides a reasonable travel time of about 13 years. The estimated cost of the mission, as discussed in the decadal survey context, falls in the flagship category, the most expensive tier of NASA planetary science missions, comparable to what was spent on Curiosity or Cassini. Flagship missions require sustained funding commitments over decades, including the development phase, the flight operations phase, and the science analysis phase. They require international partnerships to spread the cost and expertise. They require political will to maintain funding through multiple congressional budget cycles and multiple presidential administrations. All of that is challenging, but the Decadal Survey's endorsement provides the scientific community's clearest possible signal that this mission is worth those challenges. And the history of flagship missions, Voyager, Galileo at Jupiter, Cassini at Saturn, Curiosity and Perseverance at Mars, New Horizons at Pluto, is a history of enormous scientific return on investment, discoveries that redefined our understanding of the solar system and generated decades of follow-on research. A Uranus orbiter would stand in that tradition. Before we close, let's take a final sweep through the catalogue of weirdness, the things about Uranus that, when you list them all together, make it stand apart from every other object in the solar system. It rolls on its side at 97.77 degrees, an axial tilt so extreme that nothing else in the solar system comes close, likely the result of a collision with an Earth-sized object 4 billion years ago. Its poles experience 42 years of continuous sunlight, followed by 42 years of total darkness, creating seasons unlike anything else in the solar system, each lasting roughly 21 Earth years. Its atmosphere is the coldest of any planet in the solar system, at roughly -224 degrees Celsius, colder even than Neptune, which is much farther from the Sun, and the reason for that coldness is not fully understood. It radiates almost no internal heat, alone among the giant planets, and the mechanism by which the internal heat is trapped or suppressed is one of the great unsolved questions in planetary science. Its upper clouds contain hydrogen sulfide, making its atmosphere smell like rotten eggs, confirmed by telescope in 2018, in contrast to the ammonia clouds of the gas giants. Its interior almost certainly contains diamonds raining down through compressed icy fluid, a process confirmed in miniature by laboratory laser experiments in 2017. Its magnetic field is tilted 59 degrees from its rotational axis and offset from the center of the planet, creating a magnetosphere that tumbles erratically through space as the planet rotates, unlike any other magnetic field in the solar system. Its 13 rings are among the darkest objects in the solar system, reflecting only 2 to 3% of light, darker than coal, discovered in 1977 when they blocked a star's light in a brief occultation event. Its 27 known moons are all named after characters from Shakespeare and Alexander Pope, unique in the solar system, and include Miranda, a body with one of the most dramatic cliff faces in the solar system, and a patchwork geological surface that looks like it was assembled from parts of different worlds. It has been visited by exactly one spacecraft, for a few hours, more than 38 years ago, and nothing has been back since. And the next visit, when it comes, may reveal all of these mysteries to be simpler than we thought, or far stranger than we imagined. That's Uranus, the most bizarre planet in the solar system, the seventh from the Sun, the first found with a telescope, the one rolling sideways through space at 6.8 kilometers per second, the one a musician in Bath, England, accidentally found one March night in 1781, and the one that we are, finally, beginning to take seriously. William Herschel died not knowing his planet's interior might hold falling diamonds. He died not knowing its clouds smelled of sulfur. He died before the rings were discovered, before any of its moons beyond Titania and Oberon were found, before the axial tilt's implications for its seasons were worked out in detail. He died knowing he had found something real and important and strange, and that was enough for him. The science he started is still going. The planet he found is still rolling sideways through the dark, 2 billion kilometers away, patient and cold and full of secrets. And somewhere in the world, right now, there are scientists calculating trajectories and drafting mission proposals and writing grant applications and doing the slow, essential work of getting humanity back to Uranus. When they get there, the planet will have been waiting for them for longer than any of their lifespans. It was waiting before they were born. It will still be waiting when they're gone. That's what the solar system is like, on its own timescale. Patient, old, strange, and for anyone paying attention, endlessly, inexhaustibly worth knowing. There's a version of the future that's worth holding on to. It's 2047 or 2048, and a spacecraft that left Earth in the early 2030s has finally slowed itself into Uranus orbit. The news covers it the way they covered New Horizons at Pluto in 2015. Briefly, excitedly, then moving on. But the science teams watching their instruments light up with data for the first time in real-time orbit don't move on. They stay, they watch, they process, and one by one, the questions that have been stacking up since January 24, 1986, begin to find answers. The magnetic field, finally mapped in detail, reveals whether the models about the supersonic water dynamo were right, or whether something else entirely is generating that tumbling, off-center field. The atmospheric probe sends back its last few minutes of data before the pressure ends it, and those final measurements confirm or refute what Hubble and Gemini have been inferring about the deep chemistry. Miranda's cliffs, imaged from 100 kilometers away instead of 100,000, show geological features nobody anticipated, or confirm, in jaw-dropping detail, exactly what the earlier images implied. And somewhere in the data stream, probably in something nobody was specifically looking for, the orbiter finds something new, something unexpected, something that makes the team who discovers it spend the next weeks and months arguing about what it means and whether they're reading it correctly and what the follow-up observations should be. That's what the history of solar system exploration says will happen. Every mission, without exception, has found something that wasn't expected. Voyager 2 at Uranus found those 10 new moons and 2 new rings, found Miranda's patchwork terrain, found the wildly asymmetric magnetic field. New Horizons at Pluto found mountains of water ice and nitrogen glaciers and a heart-shaped basin. Cassini at Enceladus found geysers. Juno at Jupiter found cyclones at the poles arranged in geometric patterns nobody had predicted. Uranus won't be any different. Whatever the Uranus Orbiter and Probe finds, some of it will be what the models predicted, and some of it will be something else entirely. And that something else will open a new chapter in the story of this extraordinary, sideways-rolling, diamond-raining, rotten egg-smelling planet at the edge of what we know. That's why science continues. That's why missions get built and launched and flown for 13 years through the dark. That's why we keep pointing telescopes at that pale blue-green dot in the night sky. Because the answers are out there. And because every answer we get reveals the next question. And because the universe, it turns out, is always stranger than we think. Uranus has been waiting. We're starting to catch up.